Have you ever found yourself lying on the grass on a perfect summer's day, looking up into the vast, endless expanse above? You watch the clouds drift lazily by, pure white against a brilliant canvas of blue. It is a sight so common, so fundamental to our experience of the world, that we often forget to ask a simple, yet profound question. Why is the sky blue? It is a question that has been pondered by philosophers, artists, scientists. One of the first great mysteries a child might ask, looking up with boundless curiosity. This simple query opens the door to a spectacular world of physics, written in light and air. The same science that paints our daytime sky blue also creates the fiery spectacle of sunset. As the sun dips, the sky becomes reds, oranges, pinks. How can the same air display such a dramatic shift in color? The answer isn't the sky changing, it's our perspective, and the journey sunlight takes to reach our eyes. A daily performance of light, a silent display of the laws that govern our universe. Understanding this is like being let in on nature's elegant secret. 3 key players explain it: the nature of sunlight itself, the composition of Earth's atmosphere, and the intricate biology of our eyes. The story begins 93 million miles away with our star, and ends inside our minds as we perceive color. It's a reminder that ordinary scenes hide extraordinary science for anyone who asks why. We'll unravel this question step by step. First, we'll break sunlight into its parts, revealing the hidden rainbow inside white light. Then we'll travel through Earth's atmospheric blanket and meet the tiny molecules in the air. We'll see how those particles interact with light, scattering some colors while letting others pass. We'll explain the blue of the day and the red of the evening, and we'll visit other worlds to see their skies and why Earth is special. To begin our journey into the blue of the sky, we must first look at our main character, sunlight. On a bright, clear day, sunlight appears to us as a brilliant, pure white light, sometimes with a yellowish tint. It illuminates our world, warms our skin, allows life to flourish. But this simple white appearance is a beautiful deception. In reality, the light streaming from the sun is not one single color, but a rich and complex mixture of many different colors, all blended together. Imagine an artist taking every color of paint they own, red, orange, yellow, green, blue, violet, and mixing them all together on a palette. The result would be a murky, dull color. But with light, the opposite happens. When all the colors of light combine, they create the pure, bright white light that we see. This hidden collection of colors within sunlight is known as the visible spectrum. It contains every color that the human eye can perceive. The very same colors you see in a rainbow after a storm. A rainbow is nature's own beautiful demonstration of this principle, where raindrops in the air act like millions of tiny prisms, splitting the sunlight apart and revealing its true colorful nature. Each color in this spectrum, from the deep reds to the vibrant violets, is distinct, and understanding these distinctions is the first crucial step toward understanding the color of our sky. It is the separation of these colors, caused by Earth's atmosphere, that ultimately creates the blue canvas above us. Now that we know sunlight is a mixture of colors, we need to explore what makes red light different from blue light, or green from yellow. The answer lies in the very nature of light itself. Light travels through space as a wave, much like ripples spreading across the surface of a pond. Each color in the visible spectrum corresponds to a light wave with a specific, consistent length. This is known as its wavelength. You can imagine these waves as a series of peaks and troughs. The distance from one peak to the next is the wavelength. This simple physical property is what defines the color of the light and, crucially, how it will interact with the world around it. The colors of the rainbow are arranged in a precise order according to their wavelength. At one end of the spectrum, we have red light, which has the longest wavelength. Its waves are stretched out, long and lazy. As we move through the spectrum, through orange, yellow, green, and blue, the wavelengths get progressively shorter. the waves become more compressed and frequent. At the far end of the spectrum, we find violet light, which has the shortest wavelength of all visible light. Its waves are very tightly packed, buzzing with energy. This orderly progression from long-wave red to short-wave violet is fundamental to our story. Wavelength is also directly related to the amount of energy the light wave carries. While a rainbow is nature's grand demonstration of the spectrum, scientists have a much simpler tool to achieve the same effect: a prism. A prism is typically a triangular block of clear glass or plastic. When a narrow beam of white sunlight is shone through it, a magical transformation occurs. The single white beam entering one side of the prism emerges from the other side as a beautiful, fanned-out band of colors, a complete spectrum. This process, known as dispersion, happens because as light enters the glass from the air, it slows down and bends. This bending is called refraction. It is the same effect that makes a straw in a glass of water appear bent at the water's surface. Crucially, the prism does not bend all the colors of light by the same amount. The degree to which the light bends depends on its wavelength. The long, low-energy waves of red light are bent the least, changing their path only slightly. Orange is bent a little more than red. Yellow is bent a little more than orange. Violet light, with the shortest wavelength and highest energy, is bent the most dramatically of all. This differential bending is what separates the colors, fanning them out so we can see them individually. The prism is not creating the colors, it is simply revealing the colors that were already there, hidden within the white light. This simple, elegant experiment, famously conducted and explained by Isaac Newton in the 17th century, was a monumental step in our understanding of light, and proved that white light is a composite. This discovery laid the groundwork for the entire field of optics and is essential for our understanding of the sky. The Earth's atmosphere, in a way, acts like a giant, albeit less perfect, prism. It does not separate colors by bending them in such an orderly fashion, but it does separate them through a different physical process, scattering, which also depends heavily on the wavelength of the light. Understanding the prism effect helps us solidify the core concept. Different colors of light are physically distinct and can be separated. When we see a blue sky, we are essentially seeing one part of the sun's spectrum that has been separated from the rest. The atmosphere has performed a trick similar to that of the prism, but on a planetary scale. Instead of bending the light, it has scattered the blue portion of the sunlight across the entire sky, while allowing the other colors like red and yellow to pass through more directly. This is why the sun itself often appears yellowish, not pure white. Some of its blue light has been, stolen to color the sky. Now that we have seen how white light can be split into its constituent colors, it is also important to understand the reverse process. Just as a prism can separate colors, they can be recombined to form white light again. Isaac Newton demonstrated this as well. After using one prism to split sunlight into a rainbow, he used a second, inverted prism to collect the separated colors and merge them back together. The result was a single beam of white light, identical to the one that entered the first prism. This proved that the process was reversible, and that white light was truly just the sum of all the colors of the spectrum, at least as our eyes perceive it. This concept of additive color mixing is fundamental to how we perceive light. It is different from mixing pigments or paints, which is a subtractive process. When you mix colored lights, you are adding different wavelengths together. If you were to take 3 projectors, one shining red light, one green, and one blue, and overlap their beams on a white screen, the area where all 3 colors mix would appear as bright white light. This is the principle behind the screen you are watching this on right now. The pixels in your television, computer monitor, or phone screen are made up of tiny red, green, and blue subpixels that light up in different combinations to create every color you see, including white. So, the white light from the sun is an illusion created by the perfectly balanced mixture of all visible wavelengths hitting our eyes at once. Our brain interprets this full spectrum signal as the color white. This is why clouds, which are made of water droplets, much larger than the wavelengths of light, appear white. These droplets scatter all the colors of the spectrum more or less equally. Since they are scattering the full, reconstituted mix of red, orange, yellow, green, blue, and violet light towards our eyes, our brain perceives the clouds as white, the same color as the original sunlight. This stands in stark contrast to the tiny molecules of air, which do not scatter all colors equally. This distinction is vital. The blue sky is a phenomenon of separation, while white clouds are a phenomenon of recombination. The air molecules are selective, picking out the blue light to scatter around. The much larger water droplets in clouds are non-selective, scattering everything together. By understanding that white light is simply a mix of all colors, we can better appreciate what is happening when we see a blue sky. It means that something in the atmosphere is actively removing the blue component from the direct sunlight and spreading it all around for us to see, leaving the remaining light that comes directly from the sun slightly depleted of blue. While our focus is on the visible spectrum, the rainbow of colors that paints our world, it is worth noting that this is just a tiny fraction of the total radiation that the sun sends our way. Sunlight is part of a much broader range of energy called the electromagnetic spectrum. This spectrum includes many types of light that are invisible to the human eye. On the long wavelength, low energy side, beyond red light, we find infrared radiation. We cannot see infrared, but we can feel it as heat on our skin. Further beyond that are microwaves and radio waves, which have even longer wavelengths. On the other end of the spectrum, beyond the short wavelength, high-energy violet light, we find ultraviolet, or UV, light. UV light carries more energy than any visible color, which is why it can cause sunburn and damage our skin cells. It is this high-energy light that our atmosphere, particularly the ozone layer, works so hard to protect us from. Beyond ultraviolet light are X-rays and gamma rays. Our eyes have evolved to be sensitive to only the small window of visible light, because it is the most abundant type of light from the sun that actually reaches Earth's surface. The principles of scattering that we are about to explore apply to these invisible forms of light as well. In fact, ultraviolet light, having an even shorter wavelength than violet light, is scattered by air molecules even more strongly than any visible color. This is one reason why you can still get a sunburn on a hazy or cloudy day. The scattered UV radiation is still reaching you from all directions in the sky, not just directly from the sun. This reinforces the idea that the interaction between light and the atmosphere is a physical process that depends on wavelength, regardless of whether we can see the light or not. Understanding that visible light is just one part of a larger spectrum gives us a more complete picture of the sun's energy and its journey to Earth. While our eyes are the final judge of the sky's color, the underlying physics is universal across all wavelengths. The key takeaway for our story remains centered on the visible part of the spectrum. Sunlight is a mixture of colors, from long wavelength red to short wavelength blue and violet. Having firmly established the nature of the light itself, we are now ready to examine the medium it travels through, Earth's atmosphere, and see how the two interact to create the beautiful blue sky. Having explored the true nature of sunlight, our journey now brings us closer to home, into the vast invisible ocean in which we live, Earth's atmosphere. This is the protective blanket of gas that envelops our planet, held in place by gravity. It is a dynamic and complex system, essential for life as we know it. It provides the oxygen we breathe, regulates our planet's temperature, shields us from the sun's most harmful radiation. While it appears transparent and insubstantial, this sea of air is the stage upon which the daily drama of the sky's color unfolds. It is the medium through which sunlight must pass, and its composition is the critical factor in our story. The atmosphere is not a uniform entity. It is structured in distinct layers, each with its own unique properties. The lowest layer, where we live and where virtually all weather occurs, is called the troposphere. It extends from the ground up to about 10 kilometers or 6 miles. This is the densest part of the atmosphere, containing about 75% of its total mass. Above the troposphere lie the stratosphere, mesosphere, thermosphere, and finally the exosphere, which gradually fades into the vacuum of space. For our purposes, the troposphere is the most important layer, as its density means it contains the vast majority of the air molecules that will interact with sunlight to color our sky. Imagine yourself as a tiny submarine navigating this immense ocean of air. From the ground, you look up through miles of this gaseous fluid. Sunlight, arriving from the near vacuum of space, plunges into this ocean, beginning its final journey to the surface. Although the air in the troposphere seems clear to our eyes, it is far from empty. It is a bustling, crowded environment on a molecular scale, teeming with countless trillions of particles. It is the collective effect of these individual, invisible particles that works together to intercept the sunlight and transform its appearance from the pure white light of space into the rich blue we see from the ground. This atmospheric blanket is what makes our planet's sky so special. On the moon, which has no atmosphere to speak of, the sky is always black, even with the sun shining brightly. Astronauts standing on the lunar surface see a brilliant sunset against a backdrop of infinite darkness, with stars visible even during the day. This stark contrast highlights the crucial role our atmosphere plays. It is not just a passive window to the cosmos. It is an active participant, catching the light and painting the entire dome of the sky. Our next step is to look more closely at the specific ingredients of this atmosphere, the tiny molecules that make it all happen. So, what is this air actually made of? If we could take a sample of the air around us and analyze its contents, we would find it is a mixture of several different gases. The composition is surprisingly consistent all around the globe. By far, the most abundant gas is nitrogen, about 78%. Next is oxygen, about 21%. This is the gas that is vital for our respiration and for most life on Earth. Together, nitrogen and oxygen make up a staggering 99% of our atmosphere. The remaining 1% is a mix of other gases in much smaller quantities. Argon, a noble gas, makes up most of that final percent. There are also trace amounts of other gases, including carbon dioxide, which helps regulate the planet's temperature, as well as neon, helium, and methane. For the purpose of explaining the sky's color, the specific chemical properties of these gases are less important than their physical size. The main players are the diatomic molecules of nitrogen, N2, and oxygen, O2. These molecules are unimaginably small. A single molecule of nitrogen or oxygen is just a few tenths of a nanometer across. A nanometer is 1/1000th of a meter. This means that these air molecules are typically more than 1,000 times smaller than the wavelengths of visible light. Red light, for example, has a wavelength of around 700 nanometers. Blue light has a wavelength of about 450 nanometers. This immense difference in scale is the absolute key to the entire phenomenon. The interaction between light and a particle changes dramatically depending on whether the particle is much smaller or much larger than the light's wavelength. It is this specific condition, light waves interacting with particles far, far smaller than their own wavelength, that gives rise to the particular type of light scattering that colors our sky. If the atmosphere were made of particles much larger than the wavelengths of light, like the water droplets in a cloud or the dust particles in a sandstorm, the sky would look very different. It would likely appear white or gray, as these larger particles affect all colors of light more or less equally. But because our clear, clean atmosphere is composed almost entirely of these incredibly tiny nitrogen and oxygen molecules, it creates the perfect conditions for a very selective, color-dependent process to occur. Let us now visualize the journey of a single package of sunlight as it leaves the sun and hurtles toward Earth. For over 8 minutes, it travels through the almost perfect vacuum of space. In this void, there is virtually nothing to obstruct its path. The light ray, containing its full spectrum of colors from red to violet, travels in a perfectly straight line, unchanged and unfiltered. It is only in the last few fractions of a second of its journey that things get interesting. As it enters the outermost layers of Earth's atmosphere, it begins to encounter the first stray molecules of gas. At first, the air is incredibly thin, but as the light ray plunges deeper, the density of molecules increases rapidly. By the time it reaches the troposphere, our ray of light is no longer traveling through an empty space. It is now navigating a dense and chaotic soup of nitrogen and oxygen. From the light's perspective, it is like trying to run through a crowded room. It cannot travel far before it inevitably collides with one of these molecules. But this is not a collision in the classical sense, like two billiard balls hitting each other. Instead, it is an electromagnetic interaction. The light wave's energy is momentarily absorbed by the molecule, causing the electrons within the molecule to oscillate, or vibrate, at the same frequency as the incoming light wave. This energized, vibrating molecule is now unstable. It cannot hold on to this extra energy for long. Almost instantaneously, it re-emits the energy as a new light wave of the exact same color and frequency. However, this new light wave is not necessarily sent out in the same direction as the original one. Instead, it can be radiated out in almost any direction: forward, sideways, back toward space. The molecule effectively acts as a tiny antenna, catching a light wave from one direction and rebroadcasting it in many directions. This process of absorption and re-emission is what physicists call scattering. The original ray of light has been redirected. This happens billions upon billions of times every second, all across the sky. Every single molecule of air is a potential scattering point. So the sunlight that reaches our eyes is not entirely the direct straight-line light from the sun. It is a combination of that direct light and this vast sea of scattered light coming at us from all parts of the atmosphere. The crucial question, then, is which colors from the original sunlight are being scattered the most? If all colors were scattered equally, the sky would simply appear as a bright, hazy white. The fact that it is blue tells us that the scattering process has a strong preference for a particular part of the spectrum. To better understand scattering, let us move away from molecules and light waves for a moment and use a more intuitive analogy. Imagine you are standing on a pier, watching waves roll in from the ocean. The waves are long and powerful, with a large distance between each crest. Now, imagine a single, thin wooden post sticking out of the water. As the big, long waves come in, they barely notice the post. They simply move around it and continue on their way, almost undisturbed. The post is too small to have any significant effect on the path of the large waves. Its ability to scatter the wave's energy is minimal. Now, imagine a different scenario. Instead of large ocean waves, you are looking at small rapid ripples on the surface of a pond. And instead of a single post, the water is filled with thousands of tiny pebbles just below the surface. When the small ripples encounter these pebbles, they are completely disrupted. The ripples bounce off the pebbles and are sent out in all directions, creating a complex, chaotic pattern on the water's surface. The pebbles are very effective at scattering the energy of the small ripples, because their size is more comparable to the wavelength of the ripples. This analogy captures the essence of what happens in our atmosphere. In this analogy, the long ocean waves are like the long wavelengths of red light, and the thin post is like a tiny air molecule. The red light waves are so much longer than the nitrogen and oxygen molecules that they tend to pass by them without much interaction. They are not scattered very effectively. On the other hand, the small, choppy ripples are like the short wavelengths of blue light and violet light. When these short light waves encounter the air molecules, they are strongly affected. They are absorbed, re-emitted, and scattered in all directions, just like the ripples being scattered by the pebbles. This phenomenon, where the effectiveness of scattering depends heavily on the wavelength of the wave and the size of the particle, is the central mechanism behind the sky's color. It is not a random process. It is governed by precise physical laws. The light is not being dyed blue, nor is there a blue substance in the air. Instead, the blue light that is already present as part of the sun's white light is simply being redirected and spread across the entire sky by the countless tiny molecules of our atmosphere. The sky, in essence, is a giant screen illuminated from behind, and the air molecules are the projectors, choosing to project the blue light in every direction. The relationship between particle size and the wavelength of light is the absolute heart of our explanation. The specific type of scattering that occurs when light interacts with particles much smaller than its wavelength is called Rayleigh scattering. It's named after the British physicist Lord Rayleigh, who first described it mathematically in the 1870s. He discovered a very precise and powerful relationship. The intensity of the scattered light is inversely proportional to the fourth power of its wavelength. This might sound complicated, but the concept behind it is quite simple and incredibly important for our story. It means that shorter wavelengths are scattered far, far more powerfully than longer ones. Let's break down what proportional to the fourth power really means. If you have the wavelength, the scattering intensity increases by a factor of 2 to the power of 4. 2 times 2 times 2 times 2, that's 16. Blue light has a wavelength of about 450 nanometers. Red light has a wavelength of about 700 nanometers. While that might not seem like a huge difference, the fourth power relationship magnifies this difference immensely. Because blue light's wavelength is significantly shorter than red light's, it is scattered by the tiny nitrogen and oxygen molecules about 10 times more effectively than red light is. This is the selective process we have been searching for. The air molecules show a massive preference for scattering the short wavelength end of the spectrum. When sunlight enters the atmosphere, the red, orange, yellow tend to continue on their path relatively undisturbed, much like the large ocean waves passing the thin post. However, the blue and violet are intercepted and thrown in every direction. It is as if the atmosphere filters the sunlight, picking out the blue light and spraying it all over the sky. This is why when you look up at any point in the sky away from the sun, the light that reaches your eyes is overwhelmingly blue. This is a profound and beautiful consequence of a simple physical law. The color of our sky is a direct result of the size of our air molecules relative to the size of light waves. If our atmosphere were made of different molecules, or if our eyes were sensitive to a different range of wavelengths, the sky would be a different color. It is this perfect confluence of the properties of sunlight, the composition of our atmosphere, and the biology of our vision that creates the iconic blue sky that has inspired humanity for millennia. It is a planetary scale demonstration of physics happening right before our eyes. While the tiny molecules of nitrogen and oxygen are the primary actors responsible for the brilliant blue of a clear sky, they are not the only particles present in our atmosphere. The troposphere also contains a variety of larger particles, collectively known as aerosols. These can include water droplets and ice crystals that form clouds, dust, pollen, sea salt lifted from the ocean, soot from fires, and pollutants from industrial activity. These particles are much larger than the air molecules, and they are often even larger than the wavelengths of visible light. Because of their size, they interact with sunlight in a very different way. When light hits these larger particles, it undergoes a different type of scattering, known as Mie scattering, named after the German physicist Gustav Mie. Unlike Rayleigh scattering, Mie scattering is not strongly dependent on the wavelength of light. These larger particles scatter all colors, red, green, blue, and everything in between, more or less equally. This is why clouds appear white. The tiny water droplets that make up a cloud are much larger than light's wavelength, so they scatter all the colors of the incoming sunlight together, and the reconstituted white light is what we see. It is also why a hazy or polluted sky looks paler and less blue. The presence of these aerosols explains why the sky's appearance can change so much from day to day. On a very clear, dry day with low pollution, Rayleigh scattering dominates, and the sky is a deep, rich blue. The air is clean, meaning it is composed almost entirely of the small molecules that are excellent at scattering blue light. However, on a humid or smoggy day, the air is filled with larger water vapor or pollutant particles. These particles introduce my scattering into the mix, which scatters all colors of light. This adds a white component to the scattered light, which dilutes the blue, making the sky appear paler, washed out, or even grayish. So, the color and brightness of the sky are a constant negotiation between these two types of scattering. The vibrant blue is the signature of Rayleigh scattering from the air molecules themselves. The white haze, the bright clouds, and the gray gloom of a polluted day are all signatures of me scattering from larger particles suspended in the air. Understanding this distinction allows us to read the sky and know something about the condition of the atmosphere. A deep blue sky is not just beautiful, it is a sign of clean, dry air. As we will see later, these larger particles also play a starring role in creating the vivid colors of sunsets. But first, we must delve deeper into the core process, Rayleigh scattering itself. This leads to one logical question. If violet scatters more than blue, why isn't the sky violet? Violet is scattered about 45% more intensely than blue. This puzzle needs a three-part answer that includes the physics of the atmosphere, the nature of sunlight, and the biology of the human eye. The sky ends up blue because all three factors combine. First, the sun itself. The sun emits across the visible spectrum, but not equally. The solar spectrum actually peaks in the blue-green. Critically, the sun emits far less violet and ultraviolet than blue. So right away, there's simply less violet entering the atmosphere to be scattered. Even with stronger scattering for violet, there's a head start for blue. Second, our vision. The human eye isn't equally sensitive across wavelengths. Our eyes have three cone types that respond to red, green, and blue. Our combined sensitivity peaks around green-yellow and drops off at the edges. We're especially insensitive to violet, so a lot of scattered violet reaches us, but we don't register it strongly. Our blue cones respond well, but our perception of violet is weak. Third, absorption. Some scattered violet is absorbed at high altitudes and never reaching the ground. Combine these three factors, the sun emitting less violet light, our eyes being less sensitive to it, and some of it being absorbed, and blue dominates what we perceive. Our brain reads a strong blue signal and a weak violet one, and interprets it as sky blue. The phenomenon of Rayleigh scattering explains the color of the sky, and it also changes how the sun looks to us. If you could view the sun from outside Earth's atmosphere, say from the International Space Station, you'd see it as a brilliant, pure white. That's because you'd receive the full, unfiltered sunlight spectrum, red, orange, yellow, green, and violet, all mixed together. Without atmospheric interference, our star's true color is perfect white. But from Earth's surface, the story changes. As sunlight travels through the atmosphere, Rayleigh scattering steals some of it. It removes a lot of the blue and the violet, scattering them to make the sky blue. So the direct beam reaching your eye is partially depleted of short wavelengths. It's sunlight with some blue missing. What happens if you remove blue and violet from white light? The leftover light looks yellowish. Your brain reads the altered spectrum dominated by longer wavelengths, red, orange, yellow, and sees a yellowish-white sun. That's why we draw the sun as a yellow circle. Not because the sun is truly yellow, but because our atmosphere has taken a blue tax to pay for the sky. The yellower the sun looks, the more blue was scattered away. This is stronger when the sun is low on the horizon. The thicker the slice of atmosphere light crosses, the more blue is scattered, and the redder the sun appears. So the blue sky and the yellow sun are two sides of the same coin. Both come from Rayleigh scattering. The scattered light is blue, and the remaining direct light is what's left over. They cannot exist without each other. A planetary scale demo of color subtraction and addition. Rayleigh scattering has another fascinating and less commonly known effect on sunlight. It polarizes the light. Light is an electromagnetic wave. It oscillates perpendicular to its direction of travel. Most light sources, including the sun, produce unpolarized light, meaning the oscillations happen in all directions at once, up and down, left and right, and every diagonal angle in between. Scattering can filter these vibrations, forcing oscillation along a single plane. This is polarized light, the same phenomenon polarized sunglasses manipulate. When an unpolarized sunbeam strikes an air molecule, light scattered at 90 degrees becomes strongly polarized. Imagine sunlight coming from directly overhead. If you look toward the horizon, at a right angle to the sun, the blue light will be highly polarized. Its waves vibrate preferentially in a vertical direction. Elsewhere, the sky is a mix of polarized and unpolarized light, but it is strongest in a band 90 degrees from the sun. While human eyes can't see this well, many animals can. Bees, ants, and other insects use the polarization pattern as a celestial compass. Even with the sun obscured, they can detect the polarized orientation in a small patch of blue sky and use it to navigate. This helps them find their way back to their nest or to communicate the direction of a food source. The sky becomes an invisible map in polarized light. You can see this effect for yourself with a pair of polarized sunglasses. Find a patch of blue sky about 90 degrees from the sun. Hold up the sunglasses and rotate them. You should see the sky darken and lighten as you turn the lens. The sunglasses contain a polarizing filter, and rotating it changes how it aligns with the polarized light from the sky. This simple experiment reveals an invisible property of the blue sky, a hidden navigational tool for some of nature's tiniest creatures. To truly appreciate the profound impact of Rayleigh scattering, it is fascinating to imagine what our world would look like without it. Let's consider a hypothetical Earth where the atmosphere is still present, providing us with air to breathe and protecting us from radiation. But for some reason, its molecules do not scatter light. What would a typical day look like in this strange world? When you looked up, the sun would appear as a blindingly intense, pinpoint-sharp disk of pure white light. It would be a stark, lonely beacon of brilliance. But the rest of the sky, the entire dome around the sun, would be completely and utterly black. There would be no gentle blue glow, no diffuse daylight illuminating the landscape. The only light you would receive would be the harsh, direct rays of the sun. This means that any area not in direct sunlight would be plunged into deep, dark shadow. The contrast would be extreme. Stepping under the shade of a tree would be like stepping into the dead of night. You would be able to see the stars and planets clearly, even at high noon, set against the same inky blackness that astronauts see from the surface of the moon. This world would be visually jarring and alien. The gentle ambiance of daylight, which we take for granted, would be gone. This ambient light is a direct gift of Rayleigh scattering. The blue light scattered from all corners of the sky is what illuminates shadows and fills our world with soft, indirect light. It's why you can still see clearly indoors near a window, even when you are not in the direct path of a sunbeam. Without scattering, our world would be one of brilliant glare and pitch-black shade, with no gentle transition between the two. The very concept of daylight would be fundamentally altered. Therefore, Rayleigh scattering does so much more than just give the sky its color. It moderates our visual environment, making it softer, more pleasant, and more functional. It creates the very atmosphere, in a visual sense, of our planet. The soft blue sky is a symbol of the gentle, life-sustaining nature of our world. It is the result of a delicate dance between starlight and air, a physical process that not only paints a beautiful canvas above us, but also shapes the quality of light by which we live our lives. Now that we have a firm grasp on how Rayleigh scattering creates the blue of our sky, we can begin to explore the beautiful variations we see across that celestial canvas. One of the most noticeable features on a clear day is that the blue of the sky is not uniform. If you look straight up, directly overhead, the sky is often a deep, rich, vibrant blue. However, as your gaze lowers towards the horizon, the color becomes progressively paler, fading to a much lighter, almost whitish blue. This is not an illusion. It is a real and predictable phenomenon explained by the same principles, with one new variable: the path length of light through the atmosphere. Think of the atmosphere as a blanket of a certain thickness covering the Earth. When the sun is high and you look straight up, you are looking through the thinnest possible amount of that blanket. The sunlight reaching the air molecules directly above you has taken the shortest route, and the scattered light then takes a short, direct path to your eyes. This short journey means the light interacts with fewer air molecules overall. While there are enough molecules to scatter blue effectively, other colors have less opportunity to be scattered. In contrast, when you look toward the horizon, the light has traveled a much longer, slanted path through the atmosphere. This light comes from molecules much farther away horizontally. Before that sunlight reaches those distant molecules, it had to travel a long way through the air. Then the scattered light itself has to travel a great distance through more air to finally reach you. This extended journey means the light passes a far greater number of air molecules. It's like looking through a few inches of a blue-tinted liquid versus several feet of it. This difference in path length is the key. A longer path means more scattering events. More scattering doesn't just mean more blue light is scattered. It means even the less easily scattered colors, blue, green, yellow, and even a little bit of red, get a chance to be scattered. The increased number of molecules along this long path provides enough opportunities for longer wavelengths to be redirected toward your eyes. The light reaching you from the horizon is therefore a more complex mixture. It is not just pure, preferentially scattered blue. It is a blend of scattered blue, green, yellow, and other colors. This mixing of colors is what we will explore next. The consequence of this increased scattering along the horizon path is a dilution of the color. As we know, white light is the result of all the colors of the spectrum mixing together. When you look overhead, you see light dominated by heavily scattered blue wavelengths, a deep blue. However, as you look towards the horizon, the light reaching you is a jumble of colors. It contains the intensely scattered blue light, but it is now mixed with a significant amount of scattered green light and scattered yellow light, and even a tiny fraction of scattered red light. All of these have been bounced into your line of sight by the sheer volume of air the light has passed through. This additive mixing of multiple colors has a direct effect on our perception. Just as mixing red, green, and blue light on a screen creates white, mixing scattered blue light with scattered green and yellow light begins to push the color towards white. The vibrant purity of the blue is washed out by the addition of these other wavelengths. Your brain receives this more complete spectrum and interprets it not as a deep, saturated blue, but as a pale, whitish blue. The sky near the horizon appears brighter and less colorful precisely because you are seeing a greater quantity of scattered light. But that light is made up of a more diverse and complete mix of colors. There is another factor at play here, known as multiple scattering. Light that has been scattered once can be scattered again and again. In the long path from the horizon, a blue photon is almost certain to be scattered multiple times. After several scattering events, its original direction is completely randomized. This repeated scattering further diffuses the light, contributing to the bright, hazy glow we see at the horizon. It is as if the light has been passed through a frosted glass, blurring and brightening it. This effect, combined with the mixing of colors, is what creates that characteristic pale brightness that separates the sky from the land. Furthermore, the air near the surface of the Earth, especially near the horizon, often contains more than just air molecules. It tends to hold more of the larger aerosol particles we discussed earlier: water vapor, dust, and pollution. As we know, these larger particles perform Mies scattering, which scatters all wavelengths of light more equally, essentially scattering white light. This adds yet another layer of white light to the view towards the horizon, further diluting the blue from Rayleigh scattering and enhancing the pale, hazy appearance. The closer you look to the ground, the more pronounced this effect can be, creating a bright white band just above the distant landscape. The principle of path length finds its most dramatic and beautiful expression during sunrise and sunset. At these times, the sun is very low in the sky, sitting right on the horizon. For its direct light to reach your eyes, it must travel through the maximum possible thickness of Earth's atmosphere. The light rays come in at a very shallow angle, grazing the planet and passing through hundreds of miles of the troposphere. This is a journey far, far longer than the path the light takes when the sun is directly overhead at noon. This incredibly long path has a profound filtering effect on the sunlight. As the sun's white light begins this epic journey, Rayleigh scattering gets to work with extreme efficiency. The violet and blue light, with their short wavelengths, are scattered almost completely out of the direct beam within the first part of the journey. They are scattered so many times and in so many directions that virtually none of the original blue light continues on the straight path toward your eyes. A little further along, much of the green light is also scattered away. The direct beam of light is progressively stripped of its shorter wavelengths, one by one. What is left of the original sunbeam after this intense filtering process? Only the longest wavelengths of light are hardy enough to survive the journey and continue along a relatively straight path to the observer. These are the colors that are least affected by Rayleigh scattering: yellow, orange, and especially the reds. By the time the sunlight reaches you at sunset, it has been almost entirely scrubbed of its blue and green components. Your eyes receive a beam of light that is composed almost exclusively of the warm end of the spectrum. This is why the sun itself appears as a brilliant red or orange orb when it sits on the horizon. This same effect paints the clouds and the sky around the setting sun in those glorious warm colors. The red light, orange light, and yellow light that successfully navigate the long path illuminate the clouds and atmosphere near the sun from below. These clouds then reflect this already reddened light down to your eyes, acting like movie screens projecting the fiery colors of sunset. The parts of the sky further away from the sun, which are not illuminated by this direct, reddened light, may still appear blue or gray, creating a beautiful contrast across the sky. The sunset is, in essence, the final spectacular act of Rayleigh scattering for the day. While Rayleigh scattering is the primary author of the red sunset story, dust, smoke, and pollutants often act as powerful editors, enhancing the final spectacle. These larger particles cause me scattering, which scatters light of all wavelengths with a slight preference for scattering forward. At sunset, as the long wavelength red and orange light passes through the atmosphere, it encounters these larger particles. The particles catch this already reddened light and scatter it forward toward the observer, amplifying the warm colors. This is why sunsets are often far more vivid after a volcanic eruption, which spews fine ash particles high into the atmosphere, or in areas with higher levels of pollution or desert dust. These particles provide additional surfaces for the red and orange light to scatter from. They take the long wavelength light that survived Rayleigh filtering and spread it out, creating a diffuse, widespread, intensely colored glow. A clean sunset in very dry, particle-free air might be a simple yellow or orange. A dirty sunset can be a spectacular blood-red affair that paints half the sky. This explains why clouds near the setting sun light up so brilliantly. The water droplets in clouds are perfect scatterers. Direct reddened sunlight travels toward you and passes through these clouds. The droplets catch the red and orange light and scatter it in all directions, including down to you. This creates the classic fire in the sky effect, the undersides of clouds glowing with impossible intensity. They are not generating light, they are simply catching the last reddest rays of the sun and scattering them across the sky for us to see. So, the perfect sunset is a collaboration. Rayleigh scattering filters out the blues and greens over a long path, leaving warm colors. Then, me scattering from aerosols and clouds takes over, catching the pre-filtered red and orange light and diffusing, spreading, and intensifying it for observers on the ground. It's a two-stage process that transforms the sun's white light into a breathtaking display. Next time you see a spectacular sunset, remember to appreciate the intricate dance between the smallest molecules in our air and the larger particles of dust and water. It's quite something. Our journey to understand Earth's blue sky reveals just how special our planet is. The color of a planet's sky is a direct fingerprint of its atmosphere, its density, its composition, and even the dust suspended within it. By applying the same principles of light scattering, we can travel across our solar system and imagine what it would be like to stand on other worlds and look up. These alien skies provide a stunning context for appreciating our own. They show us that a blue sky is not a universal constant, but a rare and beautiful consequence of Earth's unique conditions. It is a cosmic exception, not the rule. Let's first travel to our celestial neighbor Mars. The red planet has a very thin atmosphere, less than 1% the density of Earth's. It is composed mainly of carbon dioxide. While there is some Rayleigh scattering, the atmosphere is so tenuous that the effect is weak. The dominant feature of the Martian sky is the fine, reddish dust that is constantly suspended in its atmosphere. These dust particles are much larger than air molecules, so they cause scattering, which scatters all colors, but tends to scatter red light forward towards an observer. As a result, the daytime sky on Mars is not blue, but a hazy butterscotch or pinkish-red color. The sky itself carries the same color as the planet's rusty surface. Now, let's journey to Venus, a world shrouded in mystery. Venus has a tremendously thick and dense atmosphere, about 90 times more massive than Earth's, composed almost entirely of carbon dioxide with clouds of sulfuric acid. Sunlight struggles to penetrate this oppressive blanket. The dense CO2 molecules scatter blue light so effectively that almost none of it makes it to the lower atmosphere. By the time you reach the surface, the light would have been scattered and filtered so many times that only the longest wavelengths would remain. Standing on Venus, you would see a dim, crushing, and gloomy world, illuminated by a diffuse reddish-orange glow from a sky that never clears. Finally, consider a world with no atmosphere at all, like our own moon or the planet Mercury. Standing on the lunar surface, as the Apollo astronauts did, the experience is profoundly different. Even with the sun shining with incredible intensity, the sky remains a perfect, unchanging black. There are no air molecules, no dust, no particles of any kind to scatter the sunlight. The light travels in a straight line from the sun to the surface, and that is it. There is no diffuse daylight, no color to fill the void. The stars are visible even during the day. This stark, silent blackness is the default state of a sky in the vacuum of space, a powerful reminder that our sky's color is a gift from the very air we breathe. Our tour of the solar system brings us back to Earth with a renewed sense of wonder. We have seen that the color of our sky is the result of a delicate and beautiful series of coincidences. It is a story that requires every element to be just right. It begins with our sun, a star that bathes our planet in a brilliant white light, rich in all the colors of the rainbow. This light then travels to a planet with an atmosphere that is thick enough to scatter light effectively, but thin enough to remain transparent. The composition of this atmosphere is also critical. The air on Earth is dominated by nitrogen and oxygen molecules, which are the perfect size to trigger the highly selective process of Rayleigh scattering. This process has a strong preference for the shortest wavelengths of light. It seizes the blue light and the violet light and sprays them across the sky in every direction, filling the dome of the heavens with a vibrant, diffuse glow. This cascade of scattered light paints our world in its signature color, creating the soft, ambient daylight that illuminates our lives. And finally, the story concludes with us, the observers. It is shaped by the unique biology of our own eyes. Our eyes are particularly good at detecting blue light, while being less sensitive to the even more scattered violet light. This quirk of our evolution means that we perceive the sky as a pleasing, calming blue rather than a violet hue. It is the perfect collaboration between the physics of light, the chemistry of our atmosphere, and the biology of our perception. Change any one of these factors, and the masterpiece of the blue sky would be completely different. In summary, the reason the sky is blue is beautifully simple at its core. Sunlight, a mixture of all colors, enters our atmosphere. The tiny molecules of air scatter the short wavelength blue light much more effectively than the long wavelength red light. This scattered blue light comes to our eyes from all directions, making the entire sky appear blue. At sunset, the light travels through more atmosphere, and so much blue light is scattered away that we are left with only the reds and oranges. It is a single, elegant physical principle that explains the sky's color in all its magnificent daily variations, from the pale blue of the horizon to the fiery spectacle of sunset. Well, it's rather marvelous. The quest to understand the blue of the sky is more than just a scientific exercise. It is a journey that connects us to the fundamental workings of our universe. It takes a simple, childlike question and reveals a story of immense scale and intricacy, a story written in the language of physics. We have traveled from the heart of our sun, across the vacuum of space, through the invisible ocean of our atmosphere, and finally into the complex biology of our own eyes. We have seen how a single law, Rayleigh scattering, can explain the blue of the day. It also explains the red of the evening and the whiteness of the horizon. This understanding transforms our relationship with the world around us. The sky is no longer just a passive backdrop. It becomes a dynamic canvas, a daily demonstration of the laws of nature. As we conclude our journey, it is worth remembering a few final, fascinating facts. For the astronauts orbiting our planet, they see the world from the other side of the equation. They fly in the blackness of space, looking down upon a brilliant blue marble. From their perspective, our blue sky is a razor-thin, luminous layer, the fragile, glowing skin of our living world. This is the very same layer that scatters the blue light, a delicate blanket that separates the vibrant life on Earth from the cold, dark emptiness of the cosmos. It is a powerful and humbling perspective on the preciousness of our atmosphere. So, the next time you find a moment to step outside and look up, pause and reflect. Remember the incredible journey that light has taken to reach you. Remember the countless invisible molecules in the air, each playing its part. The blue of the sky is a reminder that our universe is governed by elegant and understandable laws, and that even the most common, everyday phenomena are filled with a deep and profound beauty. The sky is not just blue, it is a masterpiece of physics, a constant invitation to remain curious and to never stop asking, why? Keep wondering.